Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, Nico and I chat with Matthew and Albert from Nethermind. We cover some of the research topics they are exploring at Nethermind before diving back into the topic of lattice-based zk systems. Matthew and Albert have been implementing LatticeFold, a folding scheme that is built using lattices. And in this conversation, we tease out some of the challenges and opportunities that such a system introduces. Quick note, I'll be taking the next 2 weeks off the show, and we'll return with regularly scheduled episodes on June 4th. In the meantime, do check out our YouTube channel. There you can find the videos from ZK Summit 13. So if you missed the event or just missed a few talks while you were at the event, you can see them there. And do remember to subscribe. There is also another event coming up. There's a ZK Hack Hackathon happening on June 20th to June 22nd in Berlin this summer. So if you're looking to jump into ZK and actually start building with this stuff, this would be a great place to check it out. Find out more at zkberlin.com. Now here is our episode. Today, Nico and I are here with Matthew and Albert from Nethermind. Welcome to the show, Matthew and Albert.
Great to be here.
Thank you. It's a pleasure to be here.
Amazing. Hey, Nico.
Hey, Anna. Hey, Albert. Hey, Matthew.
So we recently did an episode on lattice-based ZK systems with Vadim from IBM Research. And in that episode, we really did an intro to lattices and how bringing them into a snark context is a challenge, but also has some amazing payoffs. In today's episode, we're going to be diving a bit deeper into some of the cutting-edge constructions. We're going to talk about LatticeFold, a folding scheme that relies on lattices in a major way, the challenges of implementing these types of lattice systems, and hopefully do a deeper look into where the space is moving. I think a way to think about this is the first episode was from the lattice perspective looking into ZK, and this time I think we're coming more from ZK looking into lattices. I also know that at Nethermind, you've been producing a ton of great research, so hopefully we also get to talk a little bit about that later on in the show. So let's jump in. I think a good starting point would be some quick intros. Albert, you've already been on the show. You were here actually talking about the security of Fry. We're going to be talking about something quite different this time, so it might make sense to just share with the audience what you've been working on, kind of what your focus is today.
So when I was at the podcast the first time, besides talking about the Fiat-Shamir security of Fry and Starks, we also talked about proving statements over rings, for example. This is one of the problems we've been working on over these 3 years, and recently we published our conclusion to this work, which is called Zinc. Mm-hmm. It's available online. We are quite excited with it. We have also been working on, lattice-based folding. We implemented LatticeFold. We've been doing some internal research around it. We also looked at lookup arguments and how to fold them. We published a folding scheme for lookup arguments called Fly with Ignacio. We are also working on zkML. We have several ongoing projects. We are working on it from different sides. We are trying to do proof of inference via folding because in ML there's lots of repeated computations. So the circuit in a large language model or a machine learning model is it consists of a lot of layers, right? And each layer is the same as before, but with different inputs. So it's very amenable to folding. So we have an engineering team on that right now.
That's really cool. If I remember correctly, there was a project called Zater that did this back with like the very first version of Nova and R1CS. So there's a lot of new tooling since. It would be super interesting to see what you guys get up to.
Yeah. We are also exploring other ways of doing things like inference of ML, but without actually proving the entire ML model, like trying to be a bit smarter rather than just proving the whole thing. Because for some applications, proof of inference will never be fast enough. And let's not talk, like if we go into proof of training, then that's a complete mess. So we are trying to look at smarter ways to go about it, to achieve a similar result without actually proving the entire thing. And yeah, we've continued looking at several security questions around Fry.
And very important, you recorded a ZK whiteboard session.
Oh, yes.
Yeah, that was the highlight of these 3 years. Yeah, for sure.
We can link to that as well. It came out in season 2 just recently. All right, Matthew, this is the first time we're meeting. Why don't you share a little bit about the work you've been doing, what your role is at Nethermind, and kind of maybe your interaction with lattice-based systems as well.
Hi, my name is Matthew. I'm a cryptography engineer at Nethermind. I joined as an intern just after I graduated last year, and they've been kind enough to keep me on. When I was an intern and also towards the beginning of my full-time tenure, I worked on the LatticeFold project, so very much to do with lattices and the folding techniques we'll hopefully be discussing later. I also did a bit of work researching the PQ signatures, the Postquantum signature work that we're doing. And as of late, I've been working on the Zinc project with Albert. It's a new proof system that's currently online as of 2 months ago.
Nice.
So the first thing I wanted to ask you guys is sort of what does the landscape of lattice-based ZK look like today? Is it all folding or is there very different techniques? And in general, how does it compare to like pairing-based or hash-based techniques?
Okay, so this is a long question to answer. Like, it's a question that has a
short question
long answer,
with a long answer.
Yes, yeah.
Good.
And there's two questions in it, right? There's what has been done so far and how does it compare to other existing schemes. You could write papers about how lattice-based schemes compare to elliptic curve-based schemes or hash-based schemes. But let's try to answer. So there's one area of development that's related to folding, right? There's all these new schemes that are based on lattices. They are folding schemes based on lattices, which I think they have kind of become a hot topic lately in the space. I hear a lot of people mentioning them, and I see there's a lot of interest in them. Outside of folding, I'd mention Labrador and Greyhound as very exciting developments. So Labrador is a snark that's relies on lattices. The main feature of Labrador is that it produces very small proofs, and the main drawback is that it has a linear time verifier. So it's not a succinct proof system, but if you care about succinctness, Labrador might be a great wrapper around something that is succinct.
That's very reminiscent of like bulletproof style things in the discrete log setting, right? Where you have tiny proofs, but a linear time verifier.
Yeah, Labrador, in fact, is some kind of bulletproof scheme, but ported to lattices, which uses a very interesting technique, which is called Johnson-Linderstrauss lemma for proving norm bounds. Greyhound is a polynomial commitment scheme that uses Labrador as a wrapper to reduce proof sizes. And yeah, Greyhound, I think, is an extremely exciting... Well, I find Greyhound a very exciting PCS. It's a PCS based on lattices. It has... The numbers published in the paper are really good, both in terms of proving time, verifier time, and proof size.
And I think this is one Dan refers to mostly in his episode end of last year on lattices.
Can I just do a quick word check? And maybe I do know this, but PCS, what does that stand for?
Yeah, it's a polynomial commitment scheme.
Oh, okay. Got it.
Yeah, the polynomial commitment scheme is kind of the key piece of a snark. It's the most complicated one to design. It's usually the most expensive to run, etc. So if you have a nice PCS, you usually can build a nice snark.
Nice. I do know a polynomial commitment scheme I'm familiar with. I wasn't fully getting the short form, but glad you shared.
This is deep down in the lingo of ZK.
Yes. I have a pajama with PCS, the PCS words on it.
You're not wearing it right now, but that's...
No.
Good to know. The two that you just mentioned, Labrador and Greyhound, those are, as far as I understand, aren't those quite they're quite latticey, but then you have things like LatticeFold. Is LatticeFold also a continuation of that work? Is it an implementation of that work? Like how does that kind of compare?
Labrador is a proof system. It's not a snark because it's not succinct. It's a proof system that produces very small proofs. And Greyhound is a polynomial commitment scheme, which can potentially be used inside a snark based on lattices. Okay? Then LatticeFold and LatticeFold Plus and Neo and Lova are folding schemes.
Okay.
So folding schemes are not proof systems. A folding scheme is different from a proof system in the following sense. A proof system allows you to prove that certain computation was performed correctly, as listeners probably know. Or actually, it allows you to prove that you know a witness to certain NP relation, for an instance of an NP relation. A folding scheme is different in that it allows you to take two instance witness pairs or two instances, so two computations, and produce a new computation, a third one. So that is, if this third computation is correct, then the previous two were correct, except with negligible probability. So LatticeFold is a lattice-based scheme, but for solving a different problem.
Okay.
What do you mean by a different problem?
Well, the problem of designing a folding scheme or the problem of designing a proof system for an NP relation. So LatticeFold designs a folding scheme, and Labrador designs a proof system for NP relations, and Greyhound is a PCS. You can use it to compile a PIOP over a lattice to get a succinct argument for lattices.
Right. So you could use LatticeFold to combine a bunch of problems into one and then use something like Greyhound Labrador to prove that one problem.
Exactly, yeah.
And you'd have a full lattice-only stack.
Yes.
Interesting. But could you also use things like LatticeFold within existing systems? Like, do you have to have a lattice-based system in order to use that folding scheme?
No, you can potentially use LatticeFold to fold instances of your relation. And then when you are done, use a different proof system to prove the folded relation. That's actually one area we are looking in. One problem we have been studying is the problem of how to do folding in the context of Starks. So say your whole pipeline are Starks. You want to use your Stark proof system for proving your statements, but you also want to do folding, right? Maybe to reduce proof sizes. So we've proposed some frameworks that rely on lattices. So you use lattices to do the folding, and then you use your Stark proof system to prove the folded instance. Yeah, there's another natural way of going about it, which is using these hash-based folding schemes that appear recently, namely ARC and this new one, which is called Warp, I think. I think it came out on Monday. I'm not sure because there was the blackout, so I was out of AirPrint.
So we've talked a lot about different lattice schemes, and we have the proving schemes, the folding schemes. What does the tooling look like right now? Say I'm a developer and I want to work with lattices. I've done a bit of, worked with ArcWorks maybe in the past, or Plonky 2.3, and I want to work with lattices. What can I do?
Well, so there are existing implementations of all of the basic cryptographic primitives that you'd want. So let's say you want a signature scheme. We do have the NIST finalists all have to submit an implementation, and those implementations do exist. There is some limited work going on, which is like porting those schemes to new languages. That's very, very much emerging work. And the same could be said of all of these schemes that we're talking about. So Labrador has its implementation. We've done the implementation of LatticeFold. These are very much emerging works, and the implementations are very much proof of concept implementations. If, let's say, you want to, you want to use it on like Android-based platform, there's a heck of a lot of work that's going to need to be done before we get these implementations out of the academic space. So I would say that in general, if we're talking about lattice-based ZK or lattice-based cryptography, the tooling is rather limited at the moment. The caveat I would add to that the area of cryptography or lattice-based cryptography that has attracted the interest of major tech companies is homomorphic encryption, which we can talk about later, and that has a much more developed infrastructure, more developed tooling. Okay,
and so in the case of LatticeFold, do you guys start from scratch, or are you trying to normalize things?
So we did use ArcWorks libraries to a certain extent, but a lot of the work was done, completely sort of hand implementations of stuff. So ArcWorks has a field library, well known to anyone in the cryptographic engineering space. So we used their field stuff. We had to work over rings because there's lattices, and all the structured lattices work over rings, not over fields. So we had to hand implement a lot of functionality. A lot of that's open, so that's in our Stark rings library. And then, of course, the LatticeFold stuff, it's fresh out of the academic press. So that was all hand implemented.
So maybe before we dive a tiny bit more into the implementation, can you guys give us a quick overview of LatticeFold? Like, what are the main components and how to think about it from a high level?
The folding technique. Maybe where does it come from if it's taking from any other previous system as well?
Right. So the folding technique, I think, was introduced by Valiant in 2008. And before it has been ported into the post-quantum space, so via lattices, I had some work via elliptic curve-based schemes called Nova and Hypernova as well, I think.
Yeah, we covered those on the show.
Fantastic. So those works very much inspired LatticeFold. but again, because it's all elliptic curve based, so not post-quantum secure. So LatticeFold was the first lattice-based folding scheme in the hope that that is post-quantum secure.
Our understanding was that it's a variant of Hypernova that's made sort of lattice friendly, but I'm not sure what that means and sort of how to think about it.
Yeah, I think that's a correct take. Let's unpack it a little bit. So let's start with Hypernova. So in Hypernova, there's lots of shenanigans going on. And then there's a very important thing that happens, which is that you take linear combination of the commitments to the witnesses. So witnesses are always committed. And when you are done folding, you linearly combine the witnesses into a new witness.
Yeah, so we do witness plus something random times the other witness.
Yes. And the verifier gets a commitment to this new witness using the fact that group-based commitment schemes are homomorphic. And this means that the sum of two commitments is the commitment of the sum. So if you commit to two vectors and you sum them, you get the commitment to the sum of the two vectors.
I was going to jump in with the nitpick that they're additively homomorphic. For anyone who understood that they're additive.
Yeah.
So we say that the commitment is additively homomorphic because the commitment to the sum of two vectors is the sum of the commitments to the vectors. And if we replace sum by multiplication, then we say that the commitment is multiplicatively homomorphic.
But those we don't use, right? We're just focused on additive here.
Yeah, in folding, we use additive homomorphic commitments. And if they are both additive and multiplicatively homomorphic, then it's fully homomorphic. And we are very happy, but it's hard to build those. So if a verifier has commitments to two vectors, and the commitment is additively homomorphic, it can get a commitment to a random linear combination of the two vectors by randomly combining the commitments.
And this is super cheap to do because it's just I'm adding commitments together and life is good. I don't need to look at long vectors.
Yes. So this is done in Hypernova. It is a crucial step, but it is a step that's very small in Hypernova because it's extremely simple because of this homomorphism. Now, in lattices, you have a natural commitment scheme, which is called itai commitment, that works as follows. So if you want to commit to a vector of field elements, the commitment is the result of multiplying a matrix by the vector. That's the commitment. Matrix multiplication is a linear operation, so this suggests that this commitment scheme is additively homomorphic. There's a small issue, which is that because of the properties of lattices, the commitment is only binding, so it's only secure if the vector you are using has small entries.
Okay, so there's some maximum limit on how big my numbers can be, and if I go too big, I lose security.
Yes.
Okay.
So if you take a random linear combination of your two vectors, then the resulting vector might have large entries, right?
Mm-hmm.
Because you are adding the first vector and then adding a random multiple of the second vector. So you have a vector with arbitrarily large entries. So you can no longer use additive homomorphism as easily as in Hypernova when you use this commitment scheme, because you might end up working with vectors that have entries that are so large that the security of the commitment scheme is lost.
Right. And so most of the work in LatticeFold is to fix this problem?
Exactly, yeah. So LatticeFold, you just do the whole Hypernova over rings or lattices, a different structure, plus extra steps to make sure that you are never committing to vectors whose entries are too large.
And in the paper, that's called the decomposition step.
Yeah, there's the decomposition step, and there's also a norm check step, because you need to make sure that it's not only about the composition, it's also proving that the norm of what you are committing is small.
Mm-hmm. And so how does all this extra work affect sort of performance of these schemes?
Yeah, is there an improvement because of this, or does it actually hurt it?
Well, so you have to do more work, right? Because you have to do the whole Hypernova, and then you have to do extra things to make sure that you don't go beyond a certain magnitude in the entries of your vectors. So in this sense, this adds overhead.
Mm-hmm.
On the other hand, the itai commitment is particularly cheap. So there's several pros to using itai commitments and lattices that might outweigh the fact that you have to do extra work because of this non-homomorphicity.
When you say cost, are you talking speed? Is it sort of like the itai part makes it very fast, but then there's some slowdowns because of these other workarounds, basically, you need to make?
Mm-hmm. The prover has to do more work.
Okay.
Exactly, yes.
Yeah.
So in Hypernova, it turns out that the boons of at the ITI commitment are not enough to compensate for the extra work that the prover does. But if we start talking about LatticeFold Plus and Neo, or a combination of both, it seems that we get something that's possibly more performant than elliptic curve-based folding schemes.
Oh, cool.
So I was going to ask actually about the implementation itself and sort of what are the lessons that come from it. And it sounds like we're kind of skipping ahead to this, which is great. I know you also gave a talk about this topic, Albert, recently. So yeah, let's go straight to the lessons of this implementation. Like how does it compare to, I guess, folding schemes that we already have in the discrete log setting? And then how does it compare to just the almost like more brute force-ish, like I'll just do recursion of Starks, you know?
The thing is, it's kind of difficult to compare because there's lots of dimensions you might look into, right? So first thing we can say is we can talk about plausibly post-quantum security, right? Mm-hmm. So the elliptic curve-based folding schemes are not post-quantum secure, but the lattice-based ones are plausibly, and also the hash-based ones are. And you could argue that hash-based ones are more post-quantum secure than lattices, just because these lattice-based schemes rely on cryptographic assumptions that are less understood, or they are less
less battle tested.
Exactly, less battle tested. Yeah, exactly, that's the word. They rely on these lattice-based cryptographic assumptions on structured lattices, which they are not that battle tested. There's another angle, which is the arithmetization part of things. The elliptic curve-based folding schemes work over particular fields, so they are very rigid on what your computation can work on. Elliptic curve-based schemes force you to work over a large field of about 250 bits at least, because you need an elliptic curve and possibly a pairing on it, so a pair of elliptic curves. And this leads you to work with large fields because there's no small fields and pairs of elliptic curves. So working with large fields can force you to work with circuits that are larger than what you would like to. Because maybe you want to prove some computation, so a CPU computation, which is not naturally written over a large field. So you have to rewrite this computation over a large field. And then you end up working with large circuits. So even if maybe your folding scheme is very good, it's elliptic curve based, and for a fixed witness size, it's very performant. But then it turns out that for what you want to prove, you end up with very big circuits, and maybe it's not worth it. The hash-based schemes allow you to work on smaller fields, but still they force you to stay on a field, which can also lead to large circuits. But small fields are easier on the CPU.
Yeah, and you don't have this sort of overhead effect that you were talking about.
When you actually run the algorithms, but the circuit might also be bigger depending on what you are computing. Everything I said is not specific of folding schemes. Mm-hmm. It applies to any ZK system you can think of.
I want the real numbers from the implementation. I don't know the meaty stuff.
Okay, let me shut up then and give numbers. Okay, so the ITI commitment scheme is very fast.
So when you say fast, you mean compared to Merkle trees or compared to like these multi-scalar multiplications that we would do with KCG or Patterson commitments?
I mean compared to both.
Okay.
So we can compare it with hash-based commitments. The main commitment scheme we compare it to is Merkle trees, right? Because if you are using hashes, you're using Merkle trees, at least nowadays. And there's two types of Merkle trees. There's Merkle trees where the hash is a classic hash, like Keccak. And there's Merkle trees where the hash is an algebraic hash, like Poseidon 2. If you are using folding, the hash is likely Poseidon 2, because you want to recursively prove that the folding is done correctly.
So you need it to be circuit-friendly, and therefore we have one of these arithmetic hashes.
I'm reading some of our benchmarks. So I see to commit to a vector of size 2 to the 19 with a blow-up factor of 2. So we do a Reed-Solomon encoding of the vector, which is also you need to do when you work with hash-based schemes. With the Merkle tree using Poseidon 2, it took us in our benchmarks 1.8 seconds. Now, committing to 2 to the 19 field elements with ITI commitment took us around 600 milliseconds.
By the way, are these benchmarks, can we also run them? Like, can we have a link to it and put it in the show notes?
I don't think we have the link right now, but we can provide it.
That'd be amazing. Okay, so the commitment is a lot faster.
It's faster if you use Poseidon 2, if you use Keccak. So committing to 2 to the 19 field elements with a blow-up factor of 2 with Keccak is 387 milliseconds in our benchmarks. So it's half the time of ITI.
Right.
But ITI is potentially recursive friendly because it's very simple algebraically, and Keccak is not recursive friendly. And when I say that ITI is simple algebraically, I mean that if you write a circuit where you compute that the ITI commitment, so the circuit is true if the ITI commitment was computed correctly, the circuit is much smaller than if you write a similar circuit for the Keccak hash function. So it's not very practical to do recursion if you are using Keccak hashes.
Right. So do you also have like end-to-end comparisons of folding many things together, seeing how long that takes, versus recursively proving stuff with hash-based schemes?
No, we don't have
Okay.
comparisons.
I guess that'll be the next steps for those interested in contributing, right?
Yes. By the way, we welcome contributors, and maybe we can go over a list of projects we have ongoing. We are really happy to, if people is interested in tagging along, and we are completely open source, so just reach out to us and we'll be really happy to collaborate. Also on the research side of things, not only on engineering side of things.
On the Lattice front, are you doing research at Nethermind, or are you doing mostly this implementation?
We are doing some research.
Oh, so like we may eventually see a paper come out where you've like created one of these techniques or like a new system or something.
Yes. We actually spent some time thinking of a lattice-based scheme folding scheme that doesn't use sum check.
Okay.
But we eventually dropped it because we thought it wasn't going to be that much faster than LatticeFold.
Okay.
So we dropped it.
Sumcheck is hard to beat, huh?
Yeah.
We'll see where the new ones go, where LatticeFold Plus and Neo. Be interested to see if they have implementations, if and when. We'll see how fast they can go.
Who's the group who wrote LatticeFold, actually? Who is it?
It's Dan Bonnet and Binyi Chen.
Oh, yeah. Nice. Oh, yeah, we had him on.
Yes.
You talked about that. I wonder, do you know if they're doing more work in that direction? Because you mentioned LatticeFold Plus. Actually, maybe we can just quickly talk about, like, what's the difference there? What was the Plus? And which one did you implement?
Yeah, we implemented LatticeFold because at the time, LatticeFold Plus didn't exist.
Mm.
I think implementing LatticeFold Plus and Neo shouldn't be a big headache right now because of all the machinery we developed for LatticeFold.
What's the difference?
LatticeFold Plus is simpler conceptually than LatticeFold.
Oh.
LatticeFold is quite messy. So the difference between LatticeFold Plus and LatticeFold is how the range check is done. So in LatticeFold, as we mentioned, there's this extra work that the prover has to do to make sure that you are never working with vectors that have a large norm. So large norm means large entries, okay? If I say large norm, that's what I mean. So in LatticeFold, that's done. You write a grand product. So basically you write a polynomial of the form x minus 1 times x minus 2 times x minus 3 and so on, up to x minus the largest entry you want to allow in the witness. And then you prove that when you replace x by your witness, this is always 0. Okay, so when you replace x by any entry of the witness, you get a 0.
Yeah. This is our good old vanishing polynomial and zero check kind of thing, right?
Yeah, it's a grand product relation, grand product constraint, and then you use a sum check of high degree to prove that this holds for all the entries of the witness. That's how it's done in LatticeFold, and that turns out to have huge costs. So the polynomial has a big degree, unless you have witnesses whose entries are very small, right? Say that you want to allow witnesses to have entries up to 2. Then the polynomial has degree 3, right? x minus 1 times x minus 2. And then you run a sum check on a polynomial of degree 3. But if you want to allow the entries to have, say, size 2 to the 16, then you are running a sum check on a polynomial of gigantic degree, and this sum check is extremely expensive.
And why would we want bigger norms?
because at each step of the folding step, you have to decompose your witnesses into chunks with small norm and prove that these chunks have small norm.
So the bigger norm, the fewer chunks.
Exactly. You want big norms because you have few chunks, but big norm gives you a polynomial of huge degree and an extremely expensive sum check. Mm-hmm. So you have to reduce the norm, but then you have a lot of chunks, and you have to commit to each chunk.
In the implementation, sorry, I'm just going to take a little tangent while we're there. How do you deal with this trade-off, and how did you find optimal parameters for this?
I wish we could say we did it better than trial and error, but we essentially trial and error. So we did benchmarks over as many combinations as we can think of to come up with good parameters.
Nice.
We made a grid search. It's quite complicated to optimize the thing by hand, or
you can say numerical methods if you want to sound fancy about it.
Yeah.
Okay, so in LatticeFold we have this trade-off, and now you were about to tell us how it disappears in LatticeFold Plus, right?
Yeah, in LatticeFold Plus you can actually just stick to large norm, and you end up making two decompositions, like decomposing into two chunks only.
How do they do that?
It's quite technical, but what they do is they leverage the algebraic properties of lattices to create a smarter range check.
Oh.
So instead of doing this naive approach, I would say, where you write a gram product and then run a sum check on this gram product, they use tricks that are specific to lattices.
Mm-hmm. This echoes very nicely with our previous episode on lattices with Vadim Lubashevsky, who was saying, if you take existing techniques and put lattices into them, it is going to work, but you won't have something super efficient. If you really want a good lattice-based scheme, you have to design it from a lattice thinking. And it sounds like this is what happened with LatticeFold to LatticeFold Plus.
Yeah, that sounds exactly like that. Yeah, it's a very nice trick where you take your witness and you commit to a new vector where the witness appears on the top of a variable. So before you had a normal witness, and now you put your witness on the top of a variable. So each entry of the vector is x. So if your witness is v1, v2, v3, and so on, you commit to a new vector where each entry is x to the v1, x to the v2, x to the v3, and so on. And then you use some tricks related to these lattices. Lattices are basically rings of polynomials. So you use some polynomial magic to prove range checks.
You had, this is a bit of a tangent here, but you had earlier mentioned about combining folding and lookups into a construction. And we actually asked Vadim this as well. And maybe there's two questions here. One is, can you use lookups with lattices? And the second is, could you use folding plus lookups in lattices?
So I think the first question, the answer is definitely yes. Yeah.
You can use lookups within lattices?
Yes.
Or with lattices, rather?
Yes. I haven't worked out the details or thought about it at all, but I'm pretty convinced you can adapt lookup arguments to work on lattices.
Do you think it would help? Do you think it would actually be useful? Or do you think there'd be speed up? Or do you think it's like lattices are so different, such a different beast that it doesn't make sense to kind of experiment with that technique?
Well, if we have a polynomial combination scheme that's better than all others and it's based on lattices, yeah, let's say that exists, then you want to go to lattices probably because you just have the best PCS over there. Mm-hmm. Another reason you'd like to go to lattices is if you are proving lookup statements pertaining objects that live in lattices. For example, if you want to do lookups in the context of FHE, then you want a lattice-based lookup.
Interesting. So you're saying there's some certain cases where you do want to use lookups, and it would obviously help if you have a great lattice system to also use this new technique of lookups.
Yes.
In tandem with it. Okay.
And since SumCheck works over lattices, and there's lookup arguments that are based on SumCheck, for example, lasso, and we have polynomial commitment schemes for multilinear polynomials over lattices, I'm guessing that you can just write lasso over lattices and compile it with these PCSs.
What about the second part of that question where it's like you do folding plus lookups plus lattices? Like the folding plus lookups work that you did, could that be applied within a lattice context?
Yeah, I think so. But I think that folding and lookups are difficult to combine even outside of lattices.
Okay.
So one way to think about the difference between Nova and Hypernova is that in Nova you fold before you do anything. And in Hypernova, you run a bit of a proof system and then you fold.
And then you fold, so it's later in the process.
Yes. So for folding lookup arguments, you either run almost an entire lookup argument and then you do a folding at the end.
Okay.
Or you do it at the beginning, which is the work we did at Nethermind with Ignacio. It's this fly scheme that's in a print. And the folding step in this case is, if you do it at the beginning, the folding step is very cheap for the prover. But because of the nature of how lookups are expressed, when you want to prove the folded instance, it becomes complicated because you have, in our paper, there's a quadratic blowout. We discussed some ways of mitigating this quadratic blowout when you are at the proving stage or the decider phase, using another terminology. But still, it's a tricky subject. I'm not sure folding lookup arguments is a fully solved problem.
Maybe we need to figure that out first before we start applying it into a lattice context.
Yeah, I think so.
Unless, do you think this is very hypothetical, but would lattices, you talked about some of this like lattice magic, like the way that lattices are built actually open up new paradigms. Do you think there could be anything in there that could actually make such a combo easier?
That's an interesting question. Maybe yes.
Maybe that's a research question.
I think you guys should hire Anna to give you research projects.
Yeah.
to combine words and suggest ideas. Folding, lookups, lattices.
Yeah, maybe.
Make it happen.
Maybe.
You have mentioned Neo just a couple times through the conversation. It sounds like it's a new step. Actually, I think at the start you did define what it was, but can you tell me again, like, what part of the stack is Neo? Is it a system? Is it a folding scheme? Yeah, what is it?
So Neo is this paper by Wilson Nguyen and Srinath Sethi.
The usual suspects.
Yeah, usual suspects.
Nova to Neo. Yeah.
So they take LatticeFold and change a bit the way that you commit to the witness. So if you want to use LatticeFold to fold witnesses whose entries are filled elements, Neo proposes a better way to do it. In particular, it proposes a way where when you commit, you pay per bit. So if your witness has small entries, which happens a lot in many applications, when you do the commitment, you just pay for the bits that are in these entries. In LatticeFold, you basically commit to random elements. And because of that, they have very big entries. I'm not sure what's the speed up of Neo. We haven't sat down and tried to make estimates. We have made some estimates on the benefits of LatticeFold Plus. We haven't done that for Neo yet, but I think it is a really exciting work. And something that's particularly exciting about it is that LatticeFold Plus and Neo are not enemies. They are actually completely orthogonal. They are attacking two different things. LatticeFold Plus is improving the range check of LatticeFold, and Neo is improving the commitment, the way you commit to filled elements.
So you could combine them and get like a Lattice Neo Plus fold.
Yeah.
Nice.
Yeah. I'm sure there's subtleties, but it seems very doable.
Mm-hmm.
Cool.
Yeah.
How far off is an implementation of something like that? Like, given what you've already implemented, can you again use what you already have, or would you have to sort of rebuild a lot?
I definitely would be able to use a large part of our machinery, which is all open source. So, yeah, as Albert mentioned, we're talking about two different parts of the implementation. So you just be able to sort of fork hours and sort of change where you need to inside.
Nice.
You mentioned other work at the beginning of the episode. What else have you been working on, and do you want to talk about with us now?
Albert, should we talk about as well the signature stuff, which is also kind of almost more relevant to lattices as well?
Right. Yeah, our engineering team is working on aggregation of signatures for Ethereum finality purposes, right?
So lattice-based signatures?
Exactly. Right. So work that's going on is we're working on post-quantum signatures. So the concern is at the moment, obviously we're quite a heavily Ethereum leveraged company. So we're highly concerned about the advent of quantum computers, and current Ethereum signatures, the BLS scheme, are not post-quantum secure. So we're looking at ways plausibly that Ethereum could go post-quantum.
Hey, cool. The reason I'm kind of excited about that is we just did 2 episodes on quantum computing, quantum communications, and we did talk about a few of those ideas of how to transfer. We also actually talked about in the Vadim episode, like how to move, how to migrate, how to like make existing systems safe in the new world?
Yeah, a lot of them, as Nico said before, is just taking previous ideas and adapting them, like putting them in matrices and calling them lattice-based schemes. Falcon, I would say, is of that ilk, and that's what we're working on at the moment. We also think it's like a very good candidate to be the new Ethereum signature scheme. So Falcon's what we're focusing on. Essentially, a Falcon signature consists of a vector that satisfies certain constraints. And when we're looking at aggregating signatures, maybe to go back, and aggregating signatures means signing multiple things and verifying them at the same time in one shot. So there's two approaches that we're looking at. One is the Labrador scheme over Falcon signatures. Essentially, if we have multiple of these vectors, which are valid signatures, we can prove knowledge of multiple vectors at the same time using a lattice-based proof scheme. And there's a paper which discusses how to use Labrador as a wrapper around Falcon signatures to make an aggregation of Falcon signatures. And we're actually looking as well at folding Falcon signatures, these Falcon vectors together, so that you'd be able to create from multiple signatures one new signature.
I was about to ask, it sounds like there's synergy here between folding and aggregate signatures, right? Like you have many problems and you want to one-shot verify them. Yeah, the performance probably not where it needs to be in order to be like a real solution to the post-quantum Ethereum signatures. But yeah, definitely step of progress. How come the interest in Falcon over MLDSA? And I'm asking because we also talked about MLDSA with Vadim in that episode we keep referring to.
Is MLDSA, that's a signature scheme, or that's a key?
Yes. No, it's the signature scheme. It's, I think, the dilithium scheme.
Oh, sorry. Yeah, so I know as dilithium. I think originally we were very interested in looking at this paper, the Labrador wrapper around Falcon. So that sort of was literature that already existed. And that's why we sort of decided to do some engineering on that paper. Many of these papers come out without inbuilt implementations. Just if anyone's interested in getting involved in these, you pick a paper and implement it. That would be your contribution to the lattice cryptography world. So that's basically why we started focusing specifically on Falcon. And from that spawned the Falcon folding idea. Yeah, sorry, I usually call it MLDSA dilithium.
Yeah, I think Vadim was also making a conscious effort to call it MLDSA now that it's been standardized, so that people
this
stick
is like
to that.
the difference between SHA-3 and Ketchak, right? It's the same thing.
Exactly, yeah.
Oh, right, okay, fine, understood.
It's rather than using the name of the algorithm or the family of algorithms, we use the name of the standard.
So I would like to mention two projects we are very excited about. One is in the area of ML. So as I mentioned at the beginning, when you do proof of inference, proof of inference is just proving that a certain ML model outputted certain output given certain input, okay? You might want to do that, for example, if you want to authenticate that. Say you want to guarantee your users that they are talking to ChatGPT, right? So you could create a proof of inference to convince your users that that's the case. But it is extremely expensive. It is a really massive computation, and right now we are not ready to make such proofs in a reasonable amount of time. Kind of a philosophy we are taking in our team is to try to come up with light zkML solutions. So I call them light zkML solutions in the sense that instead of proving entire computations, which are massive, we try to come up with smaller computations such that proving them achieve a similar goal as the goal we had in mind initially. So let's continue with the example of authenticating a model. So now let's say that instead of doing full proof of inference, we watermark the model. So in this case, an example watermark would be, for example, we have OpenAI or the model owner have to divide all words into two lists, okay? A green list and a red list. And then we bias the model so that it outputs words on the green list more often than on the red list. You can do that and then run some tests, and you will see that the model you end up with is comparable to the original model. You don't lose much quality.
Okay, but it's identifiable in the words it chooses.
Yes. So now you want to keep the lists hidden, right? Because anybody who has the list can then create a model and bias it towards the green list and pretend it's OpenAI's model.
Mm-hmm.
So what you can do, you have OpenAI or the model owner sign the list, okay? Then it creates the inference, and it creates a zk proof that there's more green tokens than green words than red words in the output. And this way, whenever you see such a proof, you can be certain that whoever ran the model knows the green list and the red list, which means that is the claim owner.
And I guess you can even have like a public commitment to that green list, red list, and make sure the proof verifies against this commitment every time, right?
Exactly. Yeah, that's the idea.
Super cool. That's super cool.
And you end up doing a proof of membership, basically a lookup argument, right? You just do a lookup argument.
Is this something that you've released already?
No, we are implementing it right now.
Wow, super interesting.
More academic research direction we are really excited about, and we've put a lot of effort in this direction, is Zinc. Zinc is a succinct argument, or you may also call it a framework for building succinct arguments for constraints that are expressed with integers. Instead of field elements, they are expressed with integers.
Why is that desirable?
Because writing constraints with integers, so you can think arithmetic programs where the circuit values are integers instead of field elements. This is desirable because it allows you to write constraints modulo any moduli very cheaply. So you can take any circuit that uses any modular arithmetic you can think of and write it as a circuit that uses integer arithmetic, and the circuit is essentially the same size as the original one.
Okay, super interesting. So we don't have all this foreign field arithmetic issues that we usually have.
Yes. And you can use different moduli. So you can have circuits that use different moduli at different parts of the circuit and lift it to the integers, and the resulting circuit is almost the same size as the initial one.
Okay, very interesting.
Yeah, we are very excited about this because we think that there's a lot of cost being paid right now because of this foreign field arithmetic. For example, say you want to prove a zkVM instruction and you are not doing it with lookup arguments. VM instructions usually deal with bitwise operations and mod 2 to the n operations. And these operations are usually not easily writable over a field. Okay? But you can write them over the integers very cheaply, very easily. So if you want to prove VM instructions over a field, you end up proving statements of circuits that are maybe 16 times larger than the actual circuit you would write if you had integers.
Okay. And is there also an implementation underway and sort of benchmarks?
Yeah, so absolutely. We're coming towards the end of our implementation effort. We do have some benchmarks. We're going to publish them relatively soon. Albert, do we have a date when we want to publish them?
I can actually just give some numbers now.
Sneak preview for the ZK podcast.
Although by the time this comes out, they might be out. But
yeah. Yeah, let me mention also that this scheme works with hash. It relies on hashes. There's previous work for proof systems over the integers due to Campanelli and Hal Andersen. It is a framework, and when they instantiated the framework, they use hidden order groups. But hidden order groups are quite slow, and I don't want to spend too much time on that. Our scheme
is a whole other bag of beans. We've had lattices, curves, exactly, and hashes. Let's not open a new section right now.
But let's say that hidden order groups are a no-no for efficiency in this context. They are absolutely terrible. That's everything I will say. So we managed to use hash-based techniques, and it turns out that the actual scheme is very similar to other hash-based schemes that are, I would say, state-of-the-art or close to being state-of-the-art. So, for example, our polynomial commitment scheme for integer polynomials is able to commit and evaluate a polynomial with 2 to the 16 with 16 variables in a bit over 200 milliseconds. And for comparison, breakdown polynomial commitment scheme for the same number of variables on a fixed field, like the standard breakdown with a bit different code, takes 125 milliseconds in our benchmarks. So yeah, our work is less than twice more expensive. But on the other hand, it has all these arithmetization benefits I talked about.
Yes. So a 2 to the 16 circuit is going to do a lot more work than one in over fields, right?
Yeah, we believe that it equates to a 2 to the 4, 2 to the 5 speed up.
Well, okay.
In comparison. So being double as as taking double as long is negligible in those terms.
I think we are at the end of the episode. I want to say thanks so much, Albert and Matthew, for coming on the show, revisiting lattices, talking about the benefits that lattices can offer to folding schemes or vice versa. And also a lot of this new work you've been doing. Actually, I think one of my favorite parts of this episode, just FYI, was like the lay of the land of lattice and snarks, because like I don't think we actually really did that in our previous episodes. So for me, this has been really helpful. And you can also see a bit of a trajectory, like a research line: Labrador, Greyhound, LatticeFold Plus, Neo. And you also mentioned Lova. Is that a continuation on this same thread, or is it something else?
Lova is it's quite different from LatticeFold Plus, and Neo. It is modeled as Nova. So it's a Nova analog for lattices. But it doesn't work on R1CS relations. It works on a different type of relation, which I forgot which one it is, but it's still MP.
Okay.
But I'm not sure it's usable in practice.
I see.
I'm not sure.
Cool.
And it works on so-called unstructured lattices, which are supposed to be more secure than structured lattices.
Oh, that's cool.
But are less efficient.
Okay. The trade-offs. Well, yeah, thank you so much for all of that. It's been really helpful, to dig back in with you. And congrats on all of this work that's happening at Nethermind, too. It sounds very exciting there. Yeah, thank you guys so much for coming on and sharing all of that with us. It was wonderful.
Thanks a lot. It's an absolute pleasure to be here.
Thanks so much for having us.
Yeah, thank you both. This was super enlightening.
I'm glad.
All right, I want to say thank you to the podcast team, Rachel, Henrik, Tanya, and Kai. And to our listeners, thanks for listening.